So what I would like to do today is to go over the last welding processes that we have not discussed, that are beams, mostly lasers and electron beams, some chemical processes like oxyfuel, right, oxyacetylene, and if we had a chance to go over brazing. That is not welding, but it's a common joining technique too. So if you realize, when we started the class, we started saying, well, there are all these ways of putting two things together, from bolts to glues to TIG welding, right? Then we said, okay, but let's get really, really narrow on welding. Okay, and we went narrow into welding, which was typically fusion welding, and we had the arc welding processes with consumable, non-consumable electrode, with fluxes. We talked about solid state processes. We talked about electrical resistance. Poof, we talked about so many things. And there is more, right? So I want to talk about 3 more types of processes today. Beams, chemical, and then brazing and soldering, which is not welding, but is associated with it. Let's start with laser beam welding, right? The key thing of these beam processes, these high energy density processes, is that the energy, that is more or less the same energy as in TIG, is concentrated in a much smaller spot. Now the heat is so intense that it starts to evaporate the metal, right? And depending on how intense it is, it can start drilling the metal and making making a hole through, and out of this hole you have all these metal vapors coming out, right? And this is what is called a keyhole. And I mentioned to you that when people use 6010 electrode, that I don't remember if this week or next week you're going to be trying. Next week you're going to be trying that, right? Some people say, oh, here I have a keyhole. Yeah, kind of a keyhole. But this comes because you're putting an ungodly amount of power in a very small area, right? And you can imagine what you're going, the type of weld you're going to get when you have a keyhole than when you don't is very different, right? So this is the first thing to know. When you don't have a keyhole, people typically call it conduction mode, which is an unfortunate name, because the heat transfer process between the energy of the beam and the weld is convection, not conduction. Why they call it conduction, I don't know. But it's like many things in welding, it's like backwards, right? Like welding symbols, you point to one side to mean the other side, right? So here we have our plate, our substrate, and the beam comes and melts locally, right? In this case, what type of welding am I representing? It's autogenous, heterogeneous, or homogeneous? This is autogenous, right? Because there is no filler metal in this case. Same as in this other case. Which one do you think is going to have a deeper penetration? The keyhole one. Which one do you think is going to have a bigger width to depth ratio? Keyhole, big time. This can be a depth to width of a factor of 10. This is 1 or 2, right? So, or 1/2 actually, right? It's a very different type of application. So, in laser, we have molten metal and we need to protect it from the atmosphere. Typically, we do it with a shielding gas. Now, because we typically don't want an arc, then the shielding gas, we don't need to worry with the shielding gas about ionization potential and many of those other things that are so important in arc welding. Now, although I'm showing you something that is autogenous here, and that's a very common case of welding, there are many other ways of doing laser welding. For example, we can add a wire, right? If you remember when we talked about hot wire, remember that? We have 2 units of hot wire in the lab. When you have hot wire, so this is one of the things that are very fashionable these days, laser with a hot wire. You can put a cold wire. Now, there's a big difference between hot wire and cold wire. Which is going to give me a hotter weld, the cold wire or the hot wire? The cold wire needs a hotter weld because we need to melt the wire and superheat it, right? So when we have a cold wire, we either need to hit the laser on the wire, right, which is very tricky because if you remember, the wires come with a cast and a helix. So the wire comes like meandering at the very tip. And what I do is heat up the weld pool and superheat it enough to melt the wire when it comes in, right? That's very, very hot. So between hot wire and cold wire might look the same, not the same at all. And you can have what is called a hybrid laser arc. In this case, the wire comes because you are putting the wire with a MIG. So and you combine the laser with MIG, and I'm going to tell you later I'm going to tell you later like some subtleties about that. Now, you can also use it. There is another way of adding the filler material that is with powders. For example, when you're doing cladding, and when you're making a wear-resistant surface, right? You have steel, and you can put nickel tungsten carbide powders on top of it, and will be very wear-resistant, right? The laser we have in the lab. If you haven't seen it, I'll show it to you. We're in the process of mounting it. We're going to do that type of things, right? We're ready to do this cladding, right? By blowing powders. And also, a close associate of this laser cladding is additive manufacturing, what is called direct energy deposition. Many of you are working in additive manufacturing, I understand, right? And what they are called the directed energy deposition method, right? It's essentially laser cladding. But instead of making one flat surface, you just keep going and give it shape, right? In that case, for additive manufacturing, you would blow powders. You can use a hot or a cold wire. And sometimes, in the case of additive manufacturing, you can have a powder bed, right? In which, instead of blowing the powders, you just melt selectively what was in there. Of course, the polarity doesn't matter now because it's just light coming in. What are characteristics of lasers? Very expensive. If you remember when I think was our class number 3, the concept of or class number 2, we talked about how the intensity of the heat source meant so much about whether you could go fast or slow, whether it needed to be manual or automated, right? And one of the things that also the intensity of the heat source tells you is the price of the equipment, right? So lasers used to be $100,000 a kilowatt. Now it's lower than that, but it's a lot, right? Like a MIG machine or a stick welder can have many kilowatts for a couple $1,000. Right? So it's expensive. Now, because when we are focusing it, is a tight spot, it must be automated. There is another reason why lasers must be automated. Not only that it's difficult to keep track, you can say, okay, I'm going to defocus my laser and have a spot that is broad enough to be similar to TIG or MIG or something like that. Yeah, but how about reflections? One of the most difficult things with lasers, well, there are many difficult things, but one of the many difficult things with lasers is reflections, right? You realize that molten metal, especially when you're protecting it from the atmosphere, is a molecular reflector, right? It doesn't get as good as that any other way. And all of a sudden, the laser is reflecting back. There are cases, for example, if you have fiber lasers in which you might have bad luck, and the surface creates a mirror and sends the laser back through the optic fiber and destroys your laser. Isn't that crazy? Like a suicidal laser is a real problem. So if you go to industry, you're going to see that laser setups are never straight. And you say, well, why don't you make it straight? No, they don't want it straight, because if it is straight, the light can go and come back through the same hole, and with very bad consequences. Another characteristic of laser is, although it's very intense, you'd say so hot enough to evaporate, is so localized that in the end, how many joules per meter you put are low, right? That's what we call the heat input, right? The concept of welding, which we call the heat input, in laser is typically low, right? And it's a paradox. You say, oh, I have this super powerful machine that gives me low heat input, right? This is one of the many paradoxes of welding. With lasers, we can make very small details. So when we are doing repairs or wear protection or corrosion protection of things like stabilizers for SACD and drilling, laser cladding is very good because you can make the details of those parts. Efficiency in lasers, I put low efficiency due to reflections, but lasers have two problems for efficiency. One is reflection. Isn't that funny? You want to hit something with a light, but what you're trying to hit is a mirror. It's like, it's crazy. It's like trying to put glue on Teflon, right? It just doesn't go in. It's very inefficient. But in addition to that, to generate some 1 kilowatt in laser power, the lasers typically need much, much more than 1 kilowatt. And it's not that they need 20% more. They need double, sometimes 10 times more, depending on the type of laser, right? So lasers are very inefficient. This is the low, what is called the wall plug efficiency. Applications, okay, only shop welding. You're not going to see any welding rigs, right? The guy gets out of the F-250 and comes with a laser. Although, wouldn't that be a great idea if we could bring to places like Fort Mac a mobile laser unit to do in situ tasks? That would be awesome, right? I think that might be money in there. So if any of you is entrepreneurial, we can start talking. And what do you use lasers for? Well, it's exactly the opposite of welding a fence, right? Like you're welding a fence, nobody really cares. But if you're welding, you investing millions of dollars in a laser, you're going to weld the Airbus 380, for example. This double-decker Airbus, one of the reasons it's so big, and we mentioned this in the first class, is welded. But airplanes are almost never welded. Jet fighters, sometimes. But passenger planes, no. But this is welded with lasers, right? Or automotive, right, in which the car is not so expensive, but you're making millions of cars, right, and you're turning them out as sausages. You cannot afford to have either a defect, right, that stops the line, and you cannot afford also to be welding slowly. In this province, when we weld, because we typically do oil and gas, we weld very slowly, and we charge very high premiums. And when the oil price is high, everybody's happy. The oil price is low, and I don't know what we're going to do, because we don't know how to weld fast. You guys are going to be fine because you're taking this class, but everybody else before you is going to be bad. So in Ontario, for example, or in Germany, right, or in Japan, people weld with lasers very quickly, right? That's what you want in automotive manufacturing. So I forgot to connect the sound here. So let me show you our tutorial on lasers. Now I warn you, this thing I have here, not only is very old, or say, not only is aimed at technologists, not people with your level of education in theory, but also it was done like in the 80s or something. So
in laser beam welding, the heat for coalescence
this is very obsolete.
by a focused beam from a gas or solid state laser. The most commonly
This is the gas shielding, okay?
is the carbon dioxide.
This is the gas shielding. The laser is coming from there. You see this line?
Is actually a mixture of carbon dioxide, nitrogen, and helium gases. The most commonly used solid-state laser is the neodymium-doped yttrium
Not anymore.
garnet, or
Not true.
CO2 can generate greater continuous beam power and are suitable for welding thin or thick workpieces. YAG lasers generate less continuous beam power and are generally used to weld thin workpieces. Most laser welds require no filler metal, although filler metals can be used if desired. Inert shielding gases are normally employed, usually argon, helium, or a mixture of the two. Welding speeds are usually much higher than other welding processes, thus limiting heat-affected zone size and workpiece distortion. In addition, because of the intense, precisely focused heat, welds can be quite deep. Also, welds can be made in confined regions and between dissimilar metals. Laser beam welding systems are used in many industries and are typically fully automated and computer controlled.
You see a travel speed?
Equipment includes the laser and its power supply, a beam delivery system with mirrors and focusing optics, a workstation, and a motion control system to move either the laser beam or the workpiece. Many ferrous and non-ferrous metals can be joined using laser beam welding, including carbon, alloy and stainless steels, aluminum alloys, copper alloys, magnesium alloys, nickel alloys, titanium alloys, and refractory metals.
All right, so the bottom line is you can weld pretty much everything, right? And because you can make a weld that is very narrow, many of the problems of solidification are mitigated. So when you melt things and they go solid, you still have a problem. But one thing is having like a big TIG or MIG swimming pool of a molten metal that is segregating and spitting out all the alloying elements to the center. And the other is having something so narrow that there is no much room for it to segregate. There is no amount of metal that is segregating in there. So that's why it said you can weld the similar metals. So many of the problems you would have in solid state welding are minimized. Types of lasers, right? They were talking about this neodymium YAG. These are used for low powers now. They're not very popular for welding. CO2 lasers used to be popular. Those were lasers of enormous power, right? But what is now coming quite strong are these diode lasers, these semiconductor lasers. Can be a diode laser or a fiber laser that is to some extent very different, but to some extent very similar, right? They are semiconductors, like very, very powerful semiconductors. So let me tell you about these things. The first thing to pay attention is what is the wavelength of the light. Look, neodymium 1 micron, diode laser 1 micron, fiber laser 1 micron, CO2, let's call it 10 microns. Okay, what is the wavelength of 1 micron? Okay, do you guys have a sense? What is that? Is what color is it? Or is it infrared? Or is it ultraviolet? Hmm?
So asteroid goes to the red.
Right, it's infrared. That is somewhat near infrared, right? CO2 is deep into the infrared, right? And so you are not going to see either of those. However, this wavelength matters because for reasons of the physics that I don't understand yet, somehow I hope someday somebody will explain them to me. But when the reflectivity of the lasers the reflectivity of the material depends on the wavelength of the light. And the reflectivity at 10 microns is much higher than the reflectivity at 1 micron. So coupling a CO2 laser is very difficult because it bounces much more light than a diode laser or a fiber laser, right? That's one thing. There's another problem. Remember I told you you evaporate the metal? Right, so this metal you evaporate is transparent to your eyes, but in reality is somewhat opaque to the 10 microns. is somewhat transparent to the 1 micron. So one of the problems of CO2 lasers is because they reflect so much light, you need to jack up the power. And by the time you jack up the power and you start evaporating, now this relatively opaque metal plume captures the energy of the laser, and you get a plasma, which is what you didn't want to have, right? And you paid for a laser because you wanted a laser. So in addition, CO2 lasers are very inefficient for wall plug efficiency, right? To get a kilowatt of fiber lasers, you need to have like 10 kilowatts coming out of your outlet. For a fiber laser, a diode laser, you need 3 or 4 kilowatts, not 10, right? This is quite a bit of a difference. There is something else too. Most things are not transparent to infrared. For example, I don't know if you know, those who took the heat transfer class with me, glass is not transparent to infrared. Water is not transparent to infrared, right? So you make your optic fiber. It has to be transparent to the infrared, right? And you can play tricks until it's transparent to the 1 micron. But transparent at the 10 micron, very, very, very difficult. So what they do in CO2 lasers, they use systems of mirrors that the laser shoots here and mechanically hits a mirror that hits another mirror that hits another mirror, right? Now, for example, this is a real case of a company here in Alberta. They mounted the machine over a seam on the floor. So when you have the freeze and thaw during the change of season here in Alberta, the floor moves, right? Isn't that, haven't you seen that in your houses? Often some doors open different in summer than in winter. Well, now try to aim like 10 kilowatts of laser going through a bunch of gold mirrors, right? Very difficult. They are a pain. So these are pretty much obsolete because they have very high maintenance and they are not so reliable. These have many advantages, except they are so inefficient and bulky and temperamental. These other ones, fiber lasers and diode lasers, are taking over. The laser we have in our lab is what is it called? Fiber delivered diode. So it's something that falls somewhere in between these two. So what else can I tell you about this? Oh, another thing. The focus in lasers, because it's like a scalpel and you want to make small details, you want to have a beam as small as possible. But there is a limitation because your heat source, the original diode or the laser pump, has a finite size. And you'll never be able to make it smaller than that. Right? And that minimum size is what is going to control your power density. And that's going to limit you, right? If the power density is not high enough, you cannot do keyhole welding, for example. So diode lasers have like a focus of the order of 1 millimeter. That's not very tight. With these lasers, you typically cannot do keyhole welding. Fiber lasers have something that is less than half in spot. And with those, yes, you can do keyhole welding, right? So depending on the application you want, you might not have a choice. CO2, they can give you an even narrower. That's because of the physics that generate the light. CO2 lasers can give you 100 micron beam, right? Now, you can tell me, how about a 1 micron beam? Well, eventually it gets to a point in which it's a knife, right? Like you're just cutting. You cannot possibly weld. So this difference in the spot size is important. The wall plug efficiency, look at the neodymium lasers, like more or less 3%, right? Means you should have like 33 kilowatts per kilowatt delivered. Not so good. And the beam quality is not as good as the fiber lasers. Another interesting thing about lasers, if I'm telling you that the weld plug efficiency is not very good, right? And I'm telling you that to make a weld you need a few kilowatts, then very quickly you'll realize you need, for a weld of 2-3 kilowatts, 4 kilowatts, you're going to need perhaps 40 to 100 kilowatts of dissipation. Have you ever thought what that means? That's an enormous amount of energy. So very often you go to a lab or you go to a company and they show you the laser. And you think you saw everything. On the other side of the wall, they tend to have an industrial refrigeration system that is a chiller, which is enormous, right? Sometimes you have to go outside the building. One of the biggest problems when you're going to get a laser is where you put the chiller. Laser is something kind of cute and nice. In our case, for example, the laser for our lab, we're going to be using the centralized chiller of the building. So now we have a building-sized chiller. We're good, I hope. I hope nobody else gets a laser too, because it's going to get tricky. All right. So here somebody had it. Yeah.
I'm asking a question relating to CO2 laser.
Yes.
You said you have to go through a series of reflections.
Yeah, the reflections. Yeah.
What is the use of? What's the purpose of doing that?
Oh, okay. This is a purpose. Here is something you're welding. Here you have this enormous amount of machinery that is your laser. The light has to go from here to there somehow, and you cannot put an optic fiber because it's not transparent, right? And also, typically, you don't want to shoot like that because it would be very dangerous, right? And also because the way welding works, you want to work in the flat position. So you typically want the beam to come from above.
But why don't you need it in the other types of lasers? I understand.
Because the other types, yes, the other type of lasers have this wavelength that is more or less 1 micron. And the optic fibers are transparent to 1 micron.
So would the reflection reduce the microns and improve on the transparency?
Okay, so because a laser is light, it has a wavelength. Lasers are what is called monochromatic. So they have one wavelength, or a narrow distribution of wavelengths, okay? So the main difference between CO2 and all the other lasers used in welding is that the CO2 has a wavelength of more or less 10 microns. And the other ones is more or less 1 micron. At 1 micron, I can make an optic fiber that delivers things with a hose, right? And it's extremely practical. But that optic fiber is not transparent at 10 microns. So how are you going to move the light from your laser to the part? You start bouncing it on mirrors, right? That's a reason. Yeah. You could do mirrors with the other ones too, but that defeats the point, right? Yeah. So, all right. Here I have a video of laser welding. Of course, you don't see the beam, right? Because it's infrared. Isn't that interesting? Like when I showed you welding before, you would see an arc. Now you see nothing. Look at this other one here. Look how fast it's moving, right? This is a racing beam. What penetration mechanism do we have in this one at the bottom? Conduction, right? Like what people call conduction, but in reality is the beam is hitting here, and the heat goes from the surface to the sides by convection. And conduction too, but convection is a big player. Very interesting, huh? Like nothing else you had seen. Okay. Oh, let me show you about cladding. These are videos that we took long ago. We're so much better now, but I don't have those handy. Laser cladding. Cladding means to put a layer of a different material on top of a previous plate. For example, nickel tungsten carbide on steel. So this is the steel. And what you see here is the nickel tungsten carbide. And because this is going at 4,000 frames per second, so this is like 130 times lower than reality, this is moving like this, but you barely see it. You see the powders come out of the nozzle. Here you see how it is moving, right? That the plate is moving back. So the powders are coming in. What you see there bright. Do you think it's bright because of the? Do you think it's bright because of the light, the illumination of the laser? What do you think? No, because it's infrared. So why is light? Where does the light come from? Yeah, that's rather hot, right? Assuming that this is steel, which it is of the order of 1,500 degrees to start, and then up, right? So that's what we're seeing. We're seeing the radiative heat from the molten metal, right? Now look at this. Here you see those balls? That's spatter, right? That's metal that is lost. But something that worries me more than the spatter, see all these other things, the powders that never melted, and they're bouncing off the surface? Isn't that crazy? That's money lost. You shoot your powders straight on the weld pool. They should stick, but they don't. The powders that hit here in the solid, you're going to lose, we know. But the powders that go there, they should stick. Nobody knows why. It should be 100% of the powders that go to the weld pool stay, but they don't. Some amount doesn't go, right? It's not that many don't go. Why? Mystery. So about laser cladding. You have the laser and then you feed the powders, right? So the same way in MIG you feed with a wire, in laser cladding, you typically feed it with powders. And there are many ways of delivering these powders. For example, one is called off-axis. So the laser would be right here where the white separation between the photos is. The laser comes here, and you're blowing the powder right there from the side, right? That has advantages and disadvantages. The advantage is that you can make something really tiny. So if you're cladding inside a small hole, you would use typically off-axis. Now let's say we're doing a cladding of a flat surface to which we have lots of axes. Then we can have a coaxial. The coaxial means that the laser and the powders come in the same axis, right? And how does it work? Well, in this case, you have 4 holes. Our PTA torch, the one we demoed for you, has 4 holes too, right? That's what they call the discontinuous coaxial, right? And all 4 paths of powders should fall right there in the focus point of the laser too, right? You realize this is very difficult to set up. Very difficult to set up. These are called continuous coaxial. Sometimes the continuous means is continuous. You have like an annular region that blows the powder. Sometimes in reality continuous means many, many, many holes through which you blow the powders. Right, so all these type of things we have going. In our lab, we have heads for all these. They're not mounted yet. Internal cladding optics, right? You see here you have a small borehole, and you're coming in with a tool, and this tool sometimes has an optic. It has like optics at the end, and projects the light here inside. Now, this is tricky. You can imagine how hot it gets right there. And you want to put powders, and it's hot. And then you're putting many kilowatts in right, you often have a mirror here, right? Sometimes you bend the fiber, sometimes you have a mirror, but you need some sort of optics. If any powder goes back onto your optics, absorbs a lot of this thermal energy and fuses to the optics. Now the optics is ruined and it starts to absorb more energy. So it's a little bit of global warming of laser heads, dies, right? So one of the highest challenges of internal cladding is keeping the optics clean, right? And here you have the case of wire feeding. You can put the wire and the lasers in many ways, right? You can, often the laser comes perpendicular to the workpiece and the wire comes from the side. There are some optics for making coaxial wire feeding. They're experimental still, they are very expensive. I'd like to have one of those. There would be so many things that we could do with coaxial optics for laser with wire. So these things, if you go to our lab, you're going to see like this for the PTA. And I think we have like this for our laser. For this one, I don't know if we have the powder delivery system yet. Okay. So additive manufacturing, right? When you use lasers for additive manufacturing, is what you would call directed energy deposition. Here we have things like 3D printing, right? This used to be called cladding, but in this photo, clearly that's, now they call it additive manufacturing, but it's still like cladding. How many layers of cladding can you do before you start calling it additive manufacturing? Right? At some point, things merge. Remanufacturing. This is, right now we have a big project in our lab in remanufacturing or repairs, right? In sometimes a part that is tens of thousands of dollars has a little bit that is worn out or corroded or broken. Are you going to trash the tens of thousands of dollars, or you're going to try to repair it? Of course, you're going to say, I'll try to repair it. But these things have high tolerances, have very sophisticated materials. So very often, if you use just MIG or TIG, you're going to ruin it. So lasers are the way to go. Like here you have like high-speed cladding. We have two companies that do like this type of high-speed cladding. They start making something roll and go, 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 go. Another thing you can do with lasers, and this is not welding, but it's so similar to welding, I wanted to bring it up, right? Heat treatments. And this is an amazing thing because to some extent it's trivial, to some other extent is miraculous. So with a laser, let's say you don't want to melt, but where you apply the laser gets locally hot, right? And as the laser moves, the part that was hot, when the laser passed over, now it cools down. It's what is called self-quenching, because only the surface was hot, right? And then all this heat was absorbed by the substrate. Right? Those of you who did heat transfer with me, this is a semi-infinite solid problem, right? Those exact same equations of the semi-infinite solid and square root of alpha t, that's what governs the laser heat treatment, right? And you can do amazing things because instead of putting things in a furnace and quenching them, now you can do localized heating and quenching. And by tailoring how much power you put and what your travel velocity, you start tailoring the case depth and the hardness. So all of a sudden, you can make a designer heat treatment, which you cannot when you're just like tossing things into a bucket or into a furnace. Right? So you can, for example, this is a B-pillar of a car, right? I don't know if you guys know, but cars, if you look at the car from the side, and this is the front of the car and this is the back, the roof, the front of the roof is the A pillar, this is the B pillar, and then they have the C pillar, right? When you get a lateral hit, right, this is the one that protects you from the car that hits you on the side. So these are the ultra high strength steels, but they still need to have ductility, right? Ultra high, you can make it out of glass, but it would not be a good idea. So it has to be ductile. So they do these local ductility spots with laser heat treatment. Anyway, gotta love this little robot here, but it's not commercial yet. But that would be a really good idea. Huh? With one of those, you can go anywhere and do magic. All right, lasers. Laser beam welding typically has high nominal heat input. True or false? Thank you. It's false, right? Like what we were saying, it's very intense, but the area is very narrow because you move very fast. Hybrid laser arc. I mentioned to you when you combine the lasers and the arc, right? And there are two applications. For example, laser MIG, right? In laser MIG, you can, two techniques, laser MIG and laser TIG. In laser MIG has two applications. One is heavy sections. For example, with a laser, you make a keyhole so you can penetrate deeply. But one of the problems is if your fit up is not perfect, right? There is going to be a gap there, right? So with a MIG, you put filler material to fill in the space. So you get the best of both worlds. Penetration of laser, gap bridging ability of MIG, right? This is often used for heavy sections, right? Like pipeline or nuclear, although I lied. People propose this for pipeline, people do not use this for pipeline, but they would like to. For nuclear, yeah. Thin sections. So the other application is exactly the opposite. Let's not have a deep keyhole. But if I want to move faster, I need to put more heat. But if my plate is thin, right, I put heat and I can burn the plate, right? That's a case of automotive industry. So what they do is they come with a laser and they follow up with a wire. So now they can put as much wire as they want, but the melting is very localized and done by the laser, and you can go super fast, right? Laser hot wire is very commonly used in automotive industry. And in laser with TIG, the laser seems to have a stabilizing property for the arc. Then nobody understands why. Many people think they understand it, but they all have different theories that are incompatible with each other. I don't have a theory, so I can say whatever, right? But but when you're doing narrow groove, do you remember narrow groove when we have a groove that is very narrow, and we start filling it up, like not as a V, but with a number of very narrow passes. One of the problems of arc welding is that in this narrow gap, the arc wants to go to the sides, not to the bottom. And when the arc goes to one side, the other side will have lack of fusion. So with lasers, you can pin the arc right in the middle, so it will not go to one side or not to the other side. Why the laser pins the arc down, it's a mystery. But it's one of those applications for narrow gap in nuclear. The characteristics of hybrid laser arc is only automated, very high productivity, very complex to install. Now you have a laser and you have an arc and wires and lots of automation and mechanisms. Has low flexibility, right? One thing is having your stick welder, like you go weld everything anytime, and the other is setting up one of these hybrid lasers. The final weld looks just the same as a MIG or a TIG. The difference, it was done much faster. The melting efficiency is higher. I'm going to define melting efficiency later, but essentially it says, if you wanted to have a weld of this cross-section, the laws of physics tells you that you need a minimum of heat for that. Now, you always put more than that, right? The ratio between what you needed and what you put, that's the melting efficiency. The funny thing is some things like stick welding, the melting efficiency is very low. Very low. So you put lots and lots of heat and you have lots of distortions. But in lasers, especially in hybrid, the melting efficiency is quite high. Applications, large series automotive, high value added, nuclear. Look at this. This is awesome. This is, and I saw one of these live too. They are going to make a laser hybrid. You see, that's at automotive speed. That's automotive speed. Oh. Where is it? Isn't that crazy? So Tesla mastered this. When they wanted to do Model 3, that is what everybody else does. This is what is difficult. They do it right. When they wanted to do the Model 3, is when they needed to gain experience in what everybody else does. All right, electron beam welders. In electron beam welding, same as in laser, we have keyhole or conduction. Same thing, that depends on the intensity of the beam. The protection of the melt, in this case, is new. We had not talked about this before. It's vacuum. It's not a flux. It's not an inert gas. And the reason is that electrons don't travel very well in the middle of a gas. So you have to pull a vacuum. In electron beam welder, same as an SCM, same as an old CRT TV, right? You need a vacuum. So because you have a vacuum now, you have a really good protection of your melt. Things like titanium that will grab every atom of oxygen they can and ruin themselves. Like in vacuum, there's not a whole lot of atoms of oxygen to suck up. So electron beam welding being done in vacuum is a really good thing for titanium. Filler material, very similar to laser. You can be autogenous, you can be hot or cold wire. Would you do powders? I'm sure somebody would try, but all the powder feeding mechanisms I know have a carrier gas. Okay, carrier gas in a vacuum, not too good, right? So for when people do additive manufacturing in electron beam welding, they don't use these powder methods. They use they don't do the directed energy deposition methods. They would do wire added. Now, you can do powder bed manufacturing with titanium, because in this case, the delivery of the powders is not by blowing them, but just like putting them on the bed. So the polarity, right? The gun has a tungsten or molybdenum electrode, which is negative, loses electrons, and the part is positive and gets the electrons. Now, I don't know if you remember when we were doing MIG, but it's 25 volts, 30 volts, right? That number of volts. And that's why it's safe, because that low voltage doesn't penetrate your body. But in electron beam welding, you have, say, 100 kilovolts. That got interesting, right? Is not like it's enormous. It's like how many times more? Like 100 times more. Right? It's crazy, right? Like thousands of times more. Now, conversely, the current is low. So now we don't talk anymore about 100 amps or something like that. We're talking about 0.1 amp, right? So many effects like pinching and all those things. Electromagnetics is not so important now with electron beams. Very interesting. Characteristics. It's even more expensive than the laser, because now you need a vacuum chamber. It must be automated, or you must hold your breath for a long time, right? It's not a good idea. much like laser, you have a low heat input, high melting efficiency. You can make the smallest details. Now, light reflects on the surface of a molten metal. Do electrons reflect on the surface of a metal? Yeah. What do you call those?
I don't know. The reflected electrons.
Backscattered electrons. Right? That's the way a SEM works. Right? So the efficiency in electron beam welding is not 100%. But let me tell you something. There are a lot less electrons reflected than light reflected in a laser. So the coupling efficiency of an electron beam is much higher. So some metals like copper, again, for reasons that escape me, is very reflective to lasers. So welding copper with lasers is not impossible, but it's considered like something that better not. But electron beams go crazy. They don't care, right? You bring in copper or anything else. It's just the electrons coming. Of course, applications, only shop welding, very high value-added components, jet fighters. Right, jet fighter, the F-22, like jet fighters are done there. I was in the Welding Institute in the UK, in Cambridge. And I saw they had these electron beam welders with chambers in which you can put a bulkhead of a jet fighter. It's enormous. You just walk in and they're like as if like a barn door. They're enormous, right? Interesting. So, do you think electron beam welding with the fine level of detail is a manual process? What is? No, of course not. That's what I told you too. However, here is one of those things in which I wanted to tell you. Everything I tell you in this class, somebody tried the opposite. So here you have electron beam welding by hand, right? In space, it's a pretty good idea, right? Arc welding is not so advisable because not a whole lot of room to keep your gas in there, right? Stick welding, maybe, not too sure. Still need an arc. And so the Russians, and also the Americans later, said, let's try it. So this astronaut here is the second woman in space, but it's the first spacewalk by a woman. And isn't that crazy? The first spacewalk by a woman was to weld in space, to try this, to try this system. She was not very happy, because being an electron beam, if you do some stupid mistake and you end up like cutting your suit or something, that would be a pretty bad problem, right? But she did it, and it was all fine. If you see a little bit about her bio, she has one child. Can you imagine? You go, the kid goes to school and says, hey, what does your mom do? No, my mom stays home. And your dad? No, my dad is a professor. How about your mom? No, my mom is a world champion. She's been to space. She flies make fighters, right? Like, God, like, he's in the. So some people make you feel small in life, huh? So there you go. A hero of the Soviet Union. Okay, here's something about electron beam welding.
Coalescence heat is generated by the kinetic energy of a focused stream of electrons directed upon the joint. The electrons are produced by an electron gun, accelerated to high velocity, shaped into a beam by electrical fields, and then further collimated or made parallel and focused by an electromagnetic lens. This electron stream is developed in high vacuum, but actual welding can be performed in either high vacuum, partial vacuum, or standard atmospheric pressure. Because of the intense and concentrated heat generated, total heat input is low, minimizing heat-affected zone size and part distortion. This also allows for the creation of extremely deep and narrow welds. Additionally, joints inaccessible by other welding processes can be welded. Virtually all ferrous and non-ferrous metals, thin or thick, can be joined. Welding speeds are fast, and filler metal is not generally required. Equipment cost for electron beam welding is typically high, and welding is generally limited to machine parts assembled in primarily butt, corner, and lap joints.
All right. Funny enough, in British Columbia, in Vancouver, there's a company that makes electron beam welders. Isn't that crazy? How many do you sell in a year? One every odd year? I don't know. So I will switch to other types of things. This is all I wanted to share with you about beams. Do you have any questions or comments? Okay. So the good news is you're going to be very knowledgeable next time you have to talk about welding. You really know many processes. Okay, so let's talk about chemical processes. Okay, so one way of classifying the welding techniques, the welding processes, is by the source of energy. So could be an arc, could be electrical resistance, could be a high-intensity beam, right? All those things we discussed. So now, how about when the source of energy is chemical? Right? Chemical sources of energy are not intense as those that are related to electricity, right? And that's one of the reasons why people used fire for, I don't know, thousands and thousands of years. But that didn't mean that they could start joining things because they had fire, right? You needed a very intense fire. So the electric arc is like one of those very intense heat sources. The other was when people discovered acetylene. And it happened more or less at the same time as the discovery of the arc. So now they had this very intense heat source that could melt metals. So when we talk about acetylene, there are many. We have one of those in the lab too. Maybe we could demo one of those one day. I don't know.
Probably not today.
No.
I think it's been tagged out.
No, not today. Are we going to a lab today? No.
Yes.
Oh, okay. Okay, don't forget. So if so the people who do acetylene, right? They're very practical and they know lots of tricks. But the bottom line is this. So in the acetylene torch, you have two combustion stages. So you're burning this acetylene that is C2H2 that comes from the cylinder, right? And you combine it with oxygen. So you have these two. It's like epoxy glue, right? You have one cylinder and the other cylinder that they mix up, right? So they have two hoses and they go to the welding head. And what first happens is a partial combustion in which the carbon loses the hydrogen, right, and partially oxidizes and releases energy, right, and hydrogen. Now, about 1/3 of the heat of the combustion comes from this first stage of combustion. However, because that heat of combustion happens at the tip of the flame, that is very hot, right? And you see this inner core that is hot. Now, later, when the flame it combines with oxygen from the air, not the air that comes from the cylinder, not the oxygen that comes from the cylinder, it's the oxygen from the air. So it completes the combustion process and goes from CO, carbon monoxide, to carbon dioxide. and generates water and generates a lot of enthalpy. It's about 2/3 of the heat, right? And what you're going to see is these two colors, right, inside and outside. And this inner cone is the primary combustion, this partial combustion. And the outer cone is the second combustion that takes it to completion. So because you're mixing an oxidating agent like oxygen and something that is a fuel that is being combusted, and you have these valves to regulate them, you can change the stoichiometry, right? So if you have too much oxygen, right, you have obviously an oxidizing flame. That's what you want to use when you're cutting carbon steel, right? Not only you're heating it up, but you're also burning it. On the other hand, you can increase the level of acetylene, right? And you would have the inner core, the one with the acetylene, the first combustion, gets bigger, right? And the welders and the practitioners would look at the flame, would hear the type of sound that it makes. When you're reducing and the acetylene part is too big, it looks like a feather, right? That's what they call the acetylene feather, right? So this is how the chemical reactions that will give you this very intense heat. What are the advantages of this system? Well, this is even cheaper than a welding machine, right? Than an electric welding machine. You just have the cylinders. You can take it anywhere. It's very, very cheap and portable. You don't need electricity, which is an advantage. The disadvantage is the peak temperature is not very high. But it's not only because chemical flames are not so hot. It is also because this flame, right, the hot part of the flame needs to reach the metal. But guess what happens? You have a boundary layer. Again, those who took heat transfer with me remember that we talked a lot about boundary layers, right? And a boundary layer is like a layer of insulation. So is the process of heat transfer with these flames is very inefficient. If you remember, a boundary layer gets thinner with more velocity. That's the reason when there is wind, you feel it's colder. The air is at the same temperature. But when it moves fast, your boundary layer gets thinner and the heat transfer increases, right? In the welding arc, the velocity of the plasma is more or less 300 meters per second. That's very fast. You have much less in these flames. If the velocity is less, then you have lower heat transfer. In this case, you would like to have heat transfer, but you have more of an insulation. Applications. Not only you can do welding, but because the heat is diffuse, you can use it to do the preheating. You can use it to do the shaping, right? If you heat on one side of a plate more than the other, this is going to expand and it's going to start bending. That's the way you shape the steel sheets in ship making, right? Like the hull is round, especially as you come towards this bulge under the bow. You know, right? Like the ships have this big bulge. How do you make it all round? Well, with things like this, with flame forming. You can use it for cutting, right? You can use it for piercing, but for making holes, right? And also, you can use it for brazing. That I believe I'm going to have time to tell you what brazing is, right? And here you have the flame temperatures. And look at these flame temperatures of 3,000 degrees, right? 3,000 degrees. In Integra, I'll give you 20,000 degrees, right? There's no match. There's no match. The metal gets at 3,000 degrees of so hot it is the arc, right? Okay, so here they're discussing different fuels, right? But it's more or less the same. The temperatures are much lower. Questions about oxy fuel? I'm glad because I never done research on that or used it in practice. But we have one in the lab if you're curious. Let me tell you about other welding process that is based on chemical reactions. Yeah.
Can you go back to the slide? Is it only acetylene that can be used for that welding? Or like
No. All these things.
can be used?
Yes. Like map torches, I don't know if one of these is, yeah, is this map? When you buy a map torch, you can use it too. Yeah. Yeah, right? Right, natural gas. You can use it for cutting. Good? Yeah. But acetylene, look at how much hotter a flame it has than. Yeah, but still, you come with an arc and it's so much better, right? So we have fuel that burns, right? And gives me a flame, and the flame is hot and it's concentrated, and I can burn my metal and make a weld. But there's some other chemical reaction that is used for welding too, and it's a very interesting one. It's a reaction of reduction and reoxidation. So it's called thermite. You might have heard about this, right? And it's very interesting. In this case, you mix two powders, two harmless, innocent-looking powders, iron oxide and pure aluminum powder, right? That's okay, nothing happens. Now, when you ignite this reaction, right, when the reaction happens, it releases enormous amounts of heat. And how does the reaction go? The aluminum, that is a very strong oxidizer, has very high affinity for oxygen, will steal the oxygen from the iron. So it's reducing the iron and releasing lots and lots of heat, right? This is a weak oxide, this is a very strong oxide. So if I steal the oxygen from my iron, I start to have metallic iron, which at that temperature is liquid. And here you have this slag of alumina, right? And releases lots and lots of heat. Same here, you can use copper oxide and aluminum, right? The aluminum is a very strong getter. So how does it work? You mix these two powders, nothing happens. You put them in a refractory crucible, right? And imagine you want to weld, in this case they put rebar, but could be railroad tracks, right? It's very used in railroad tracks. And you ignite it. Once you ignite it, this releases energy and gets hot, and because it gets hot, it catalyzes. It's an autocatalytic reaction. So this goes white hot nearly instantly. And then the iron falls, and it's so hot that melts. But you have to be really, really hot to remelt part of this rebar here, right? And the alumina floats to the top. When this cools down a bit, you open it up, and you have a big mess of iron all around this that you have to come with a grinding machine, right? And but this is a very practical way of joining these two things, right? In this other case, this is like what they are working on railroad tracks too. They have thermite, and they have a catchment basin on the side. So applications, yeah, welding rebar, welding railroad tracks, large cross-section electrical connections, right? So thermite is somewhat similar. Do you remember when we talked about electrogas or electroslag, in which we have essentially a swimming pool of metal, right? And we have it combined. In the case of electrogas or electroslag, it was the plate on two sides and then a copper shoes on the outside. In this case, you have your rebar or your railroad tracks surrounded by all this refractory environment that will contain the molten iron that is very, very hot, right? Something people have tried, and I'll show you a video of that, is since it gets so hot and you're going to create this ceramic compound, how about if you make a metal matrix composite? for example, in this case here, well, that's what people call combustion synthesis. This is in the foundry I was running when I was a professor in Colorado. So here we have a crucible, and we have molten aluminum here. So they put molten aluminum and pellets of titanium and graphite. And the idea was that the titanium and the graphite would catalyze and become a titanium carbide, releasing lots of energy, but also becoming a ceramic reinforcement to the molten aluminum, right? So let me show you how this works. So it's red hot. There is this molten aluminum inside, and they have this tempering thing there, and they put the pellet. This black thing is the pellet of titanium and graphite, and it's going to catch on fire very soon. When, oof, there you go. There was the autocatalytic reaction, right? This was a project for the aerospace industry. Really, do you think they're going to make rockets with this technology? Right, but making this in situ preparation of ceramics. Isn't that interesting? So in addition to the standard combustion, we have these other oxidation reactions that generate so much heat. And again, when I show you equations we see later, you're going to see the same equation would apply to thermite, flash butt welding, MIG, TIG. It's quite good once we go deep. Any questions about chemical processes? All right, so I'm going to go on my last couple of slides on God, why is this so small? Okay, so this is going to be very brief. Brazing and soldering. So I want you to be aware. Brazing and soldering is to metals what gluing is to cardboard. All right. So in brazing and soldering, if you remember, I mentioned this before, we do not melt the base material. We do not melt the base material. So we have chemical reactions at the interface, but they're microscopic, right? Brazing is what your plumber does when they put the copper pipes together. Or the old school steel bicycles that they have these brazed gussets, right? They're very, very artistic. Okay, that's brazing. So it's a minimum disruption of the base metal. So you can reheat it, and that melts the braze, and you can take it apart. So it's a somewhat reversible type of process. It's not as easily reversible as nuts and bolts, but it's much more reversible than MIG and TIG. You can join very different materials, and the reason is you're not melting the materials. So if the materials are incompatible, all you need is to find a material that would be somewhat compatible with both, but it doesn't need to be compatible at the covalent bond level, right? So you can do ceramics to metals, for example, with brazing. The joint happens by the flow of the metal, and for the flow of the metal, what you need is capillary action. I'll show you more in the next slide, right? But if you wet a paper, right, you see that the water propagates through the paper. For example, a paper towel. If it is wet, the water starts to propagate, right? That's capillary action. And you do the same. You put the two parts together in brazing, and they are very, very close, and they are wetting, right? Your braze wants to touch this material being brazed. And so it starts to pull through all these cavities and goes by itself, right? These type of joints that are brazed, of course, there is a relationship between strength and melting temperature, right? This is a rough relationship, but if I do brazing, the braze is less melting temperature than the things I'm joining, and if it is less melting temperature, that also means typically weaker, right? So these type of joints perform better in shear, because in shear I can have an enormous amount of area for this than in tension, where in tension essentially is always going to be limited by the strength of the shear, the braze, and not the base metal. The equipment for manual or machine brazing is simple. So you can do it by hand, like a plumber, or you can do it automatically, like having systems in which the molten metal comes in place and goes by capillary. So how's the functioning principle? So here we have, say, one metal surface, and here the other metal surface. So there would be a plate, and the other plate with the axis pointing up. And the braze is wetting. So this wetting pulls, you can do the mathematics, but this wetting angle creates a force that pulls the material in, right? And for example, as the material pulls in, it needs to drag more and more material. So brazing starts fast, and then it starts to go slow as the capillary force needs to bring more and more material through it. And one last thing that you're going to hear is brazing and soldering are often different things, right? Soldering, you do your electronics. Brazing is the plumber and the bicycle maker. However, the physical principles are exactly the same. So much so that people cannot determine what is brazing and what is welding, what is soldering. So they say, if the filler melts above 450 C, we're going to call it brazing, and if it melts below 450 C, we're going to call it soldering, because pretty much that's no man's land. Like typically soldering happens at 100, 200 degrees, and brazing happens at 600 degrees. So this thing right in the middle is kind of, you shouldn't have much of a problem, but it's that arbitrary. All right. Any questions regarding brazing? Okay. Yes.
Does it have to be a flat configuration for brazing and soldering?
Excellent question. Doesn't have to be, but I've never seen that it's anything else. And the main reason is two flat things or with low curvature are easy to put together, pretty much in touch. If you have like a more sophisticated curvature, it can be difficult. But I am certain that there have to be applications in which things are not flat. In soldering, it's not flat at all. When you're welding your circuitry, right? It's different. Yeah?
So are there any typical materials used for brazing and soldering?
Yes, for solder you would have tin lead. And depending on the balance of tin and lead, you have the melting temperature. The eutectic there is 183 degrees. For brazing, you have silver-based fillers or copper-based fillers, right? Or tin-based fillers too, right? And they're quite standardized. There could be a course only on brazing and soldering. But I just wanted you to be aware now that we have the time. All right, let's stop here and let's go to the lab.